Hi everyone. Today I'd like to talk about normal distributions and z-scores. So a normal distribution is kind of like a bell-shaped curve, and this is a probability distribution we use for continuous variables. Now there's some important properties. So if you look at this bell-shaped curve I have drawn, you'll notice that it's symmetric. It's a mirror image of itself if I were to look at this point. So it's symmetric with respect to this point, and I'll label that point in a moment. It's got some other important properties as well. The area under this curve equals 1, which is really important when we talk about probability, and the mean equals the median equals the mode. So that's very different than these skewed distributions we have seen previously in our course. But the bottom line is we're looking at a bell-shaped curve. And this particular point in the middle here, I'm going to label with the Greek letter mu. So it looks like a U shape. The way I'm pronouncing this Greek letter, it's mu, M-U, and it stands for the mean. Now, some other notation we'll use here. I'm going to use the Greek letter, the lowercase Greek letter, sigma. So this is sigma, to represent the standard deviation. So I'll just abbreviate that standard deviation right there. All right, and that's like a little circle, a little O with a tail off the end. That's the Greek letter sigma. So when I'm looking at this curve, I'm thinking about the mean being right here in the center, and then I could measure up one standard deviation. So if I go up one standard deviation, that would be mu plus sigma, which looks kind of like crazy notation, and I'll get rid of that in a moment and relabel it something much nicer. But bear with me for a moment. So this is up one standard deviation, and what's so special about that point there, if you notice this curve, it's kind of arcing, it's going downhill, but it's kind of like a hump. And then right at this point, there's an inflection point or a toggle point, and it's still going down, but now it's kind of changed the nature of the curve in that it's concave up. And similarly, if I went at the mean and I went below the mean by one standard deviation, so if I took the mean minus one standard deviation, and I look at that point, again, there's an inflection point. What's so special about that is that we have names for these points, so we don't have to use all this kind of crazy notation all the time. I'm going to call the mean z equals 0. It's like my middle point. It's like ground zero. And then if I go up one standard deviation, I'm going to call that z equals 1. And if I go below, I'm going to call that z equals -1. Now, I could keep going here. So, for example, if I went up 2 standard deviations, that would be the awkward notation mu plus 2 standard deviations. And who needs to write that out? I'm just going to call that z equals 2. And you might imagine that there's also a z equals 3 and so forth. And similarly, you can go down the other way, and you could label this point down here below the mean by 2 standard deviations. That's going to be your z equals -2. And what's so special about measuring our data in terms of standard deviations, z equals 0, z equals 1, and so forth, is that this normal curve has been studied so much, and it has such nice properties that between -1 and 1 standard deviation of the mean, we know that 68% of the data lives in this region. And you can kind of see that, if I were measuring the heights of females in the United States, I would have an average height, and you would probably see the majority of people kind of around that height. And that's what this bell curve is saying. It's saying the majority, the 68% of the people probably are within 1 standard deviation in the mean. Now, if I went out and measured between two standard deviations of the mean, so if I go out a little bit further here, and I'm going to have to shade that a little bit different. So now I'm going to include all of this area. That region there, so I'll label it with the green, that accounts for 95% of the data. And if you went out 3 standard deviations, you would capture 99.7% of the data. So to summarize that, we've got about 68% of the data within 1 standard deviation of the mean. So that's between -1 and 1. And then we've got 95% of the data between z equals -2 and 2, and 99.7 roughly between z equals -3 and 3. But what about data points that might lie somewhere in between? So what if I had a data point that lied somewhere over here? So I'm going to show you the steps. For my problem here, I'm going to suppose that you have been given data and that you have a mean of 100, that you're told the standard deviation is 2, and that you've got an X score, you've got some data point that's sitting at 104.5. And my question for you is, what is the Z-score? So the Z-score formula is X minus mu all over sigma. So what I'm going to do is I'm going to write down the numbers on paper and then show you how to compute this using technology. So up in the numerator here, I've got X, which is 104.5, minus mu, which is 100, all over sigma, which is 2. Okay, so I'm over here at wolframalpha.com. There are many other computational tools you could use, but this is a really nice one. So up in my numerator, I'm going to put parentheses around that. I've got 104.5 minus 100 divided by 2. And I hit enter. And that tells me my result is 2.25. It's very important that you put parentheses here because you want to divide the entire numerator by 2. You don't want to just divide the last number there, 100 by 2, but you want to divide everything by 2, and that's why I include the parentheses there. So what we found is that our Z-score is 2.25. So that means I'm somewhere up here. I'm 2.25 standard deviations away from the mean. Now I'm going to go to an online Z-score calculator. I really like this one. It works on your phone as well as on the computer, and it's nothing fancy. We don't really need anything beyond what this is doing for us. So what I'm going to do here is I'm going to put in my data. I've got a mean of 0 for my Z-score. My standard deviation is 1 for my Z-score. And my particular Z-score of interest is 2.25. And so if I click recalculate, it tells me that the area to the right of that, the area in that upper little tail, is 0.0122. That's about 1% of the data is way up there. And then if I wanted the area below, let's click on this button. It tells me that about 98.78% of the data lies below. Okay, so I cleaned up our page a little bit and coming back to look at what we have, suppose I'm measuring candy bars and the average weight of a candy bar is 100 grams. And I go and I find a candy bar that is 104.5 grams. And I say, ooh, that is 2.25 standard deviations above the mean. And I say, that's kind of unusual because what we found that 98.78% of the candy bars were smaller or lesser weight. And so I have a value that's kind of extreme. And we'll talk about that later on in our course. But for now, what I want you to see is how to compute the z-score and how the z-score corresponds to a position on this normal curve, as well as the area to the left or to the right of your z-score.